So I have posted over here some new assignments. I had a couple of people that asked me about the active chemistry. It had a due date of yesterday. What was due yesterday was just get signed up and attached to the class. There are no homework assignments posted as of yet. That should change between now and Wednesday. But for right now, what I'm hoping to do is finish with section 7.2 today so that we can get into 7.3. So you're going to want to read through 7.2 again, make sure that you understand that content now that we've seen it in class, and then skim through section 7.3. I've assigned Prepare to Learn 7B. I've set that due date as Wednesday, but that's at midnight. So you don't have to do it before class. And the reason I've done that is because that also covers section 7.4. So I think you have both of those in there. So you may want to wait to do that until you've have the opportunity to look at 7.4 as well. We won't get into 7.4 until Friday. So any questions about that? So we had talked about atomic radius as far as a periodic trend. What was the part of atomic radius that was kind of counterintuitive? That is not what
as we go past a period, it gets smaller.
Right. So as we increase the atomic number in one row, you're going to have a smaller and smaller atom. So element 3 would be lithium, element 9 would be fluorine, but fluorine element 9 is actually much smaller than lithium element 3. And in fact, even if you go down the group that fluorine is in, where you're looking at very small elements within their own row, but they're getting larger as you go down, iodine as a neutral element is smaller than lithium is. So iodine is element like 53, and lithium is element 3, and yet iodine is smaller in its neutral state. Now, one of the things that we're going to look at is how turning things into ions is going to change their size. Okay, and so we said that the rationale for why this was occurring was because of shielding. So you can kind of think of the core electrons blocking the valence electrons from filling the nucleus, but the word that is used in chemistry is shielding. So that's the term that you need to know. Find where we are here. This one bigger. Trying to coordinate two things at once is a challenge. All right, and then they get bigger at the end of each row because the inner electrons are shielding the outer electrons. Okay, so the next trend we are going to look at is ionization energy. We did talk about this last fall. I know Dr. Hamilton talked about it in his class. Ionization energy is the energy that it takes to remove an electron from a neutral atom. So in this equation here, we have sodium going to sodium plus and 1 electron. And so we can talk about the first ionization energy, which makes it +1 ion, and then we could have a second ionization energy and a third ionization energy, however many it takes to make all of the positive charges. We know that sodium and all of the elements in the alkali metals, that group 1, really easily form a +1 charge. So you would expect that ionization energy to be very low, right? It should be very easy. And because we have to put energy in, it's required, it's going to be a positive energy. So anytime energy is positive, that means we have to put that energy in. Just like with endothermic being positive, you had to put heat in for an endothermic reaction. Same thing with this energy. If the energy is positive, we have to put the energy in to make this happen, but very little for the alkali metals. And then you can imagine with my noble gases that want to stay the way they are, it's very hard to remove the electrons. So very high ionization energy. So you can see the top element in each of those little groups of peaks there are noble gases, very hard. Now, if we think about this in terms of the last periodic trend, the size with the noble gases being very, very small, that means they're very, very close. The electrons are very, very close to the nucleus. And so this is kind of like a parent that is super vigilant about their kids, keeps them all very close to them. Maybe they even like, you know, or have like the backpack with a little leash that they carry around with them if they have to go somewhere. So that kid is not getting away from the parent at all. But your alkali metals are more like the parent that's like, they're good. They can play in the neighborhood. They can roam around, do whatever. You see these movies of the kids from the 50s and 60s. They ride their bikes off, are gone all day. Mom and dad don't know where they are. That's more like your alkali metals. The electrons are very far away from the nucleus, just like the kid's very far away from the parent. So it's easier for something to take that electron away. And then we have the general trend going up. Now notice how with our radius, it was pretty smooth. I mean, it kind of had a curve to it, but it was pretty smooth. This is more jagged. So we have, it generally goes up from the alkali metal to the noble gas, but there are these blips along the way in every little group here. We'll talk about those blips in just a minute. All right. So key thing to remember, lowest ionization energy for the first group, highest for group 18. And the general trend is to have higher and higher ionization energy as you go across. Okay, so the other thing that we did last fall was we used arrows to represent electrons, and we put them on these lines. That's called an orbital filling diagram. And so you might remember that we would have like one little line that would represent the 1s orbitals, and then we'd have the 2s and the 3p and so on and so forth. So what I want to do is take a look at these diagrams. Hopefully this looks somewhat familiar to you. If you were going to do oxygen, oxygen is element number 8. So you'd put in 8 electrons and you would show them like this. What we did last fall is we then said, okay, well, what are the 4 quantum numbers of one of these arrows? Key thing is to remember that the arrows represent electrons and the lines represent orbitals. And so the top orbitals that have anything in them are the valence orbitals, or where the valence electrons are. So the difference between where those electrons are and the top of this graph is the ionization energy. So the top of the graph has a little 0 next to it. So that means there's 0 energy. It doesn't take any energy to take an electron from that point away from the atom. And so essentially that means the electron's so far away, the atom can't tell that it's there. The attraction between them is so weak that it's negligible. So if we were to take something from, say, the 3D on this graph instead of the 2P, you can imagine the ionization energy would be less, right? And if we were to try and take one of the core electrons, ionizing one of the core electrons would be a greater ionization energy, okay? So little ionization energy has to do with the orbitals being higher up. A lot of ionization energy has to do with the orbitals being down low. All right, so here's that graph again, and then we've got another representation here of ionization energy. Sometimes I feel like the one on the right is a little bit easier for people to kind of appreciate how the ionization energy works. So you can kind of see how it's very low on the lower right-hand side, and then it's very high on the left-hand side, and then higher at the top. Now notice hydrogen is behaving a little bit differently than the rest of its group, or its group. So it's quite a bit higher, and it would fit in more around where, say, nitrogen would be for its ionization energy, pretty comparable to nitrogen. So this is another way I keep saying hydrogen is a problem child. It behaves a little bit differently than all the other things behave. And we're going to have that keep coming back again and again. Okay, so the trend is across the period from left to right, the ionization energy increases. So as size gets smaller, ionization energy goes up. And then down the group, ionization energy decreases. So as size goes up, ionization energy goes down. And the reason these run in opposite directions is that the closer the electron is to the nucleus, the harder it is to take that electron away from the atom. So we don't often deal with ions, but we're going to be, after we finish with this, we're going to be getting into bonding. And so all of this stuff with the attraction of electrons is going to be directly related to bonding and how the electrons behave in bonds and how we can tell the difference between metals and nonmetals and those kinds of things. So keeping in mind what's big and what's small, what easily gives up an electron and what doesn't, is going to help us to understand how the elements behave in bonds. All right, so let's take a look at a trend here. So what I want to notice is particularly where we had that little blip, the first little blip going across the periodic table. So it was generally an upward trend, but we had lithium and then beryllium was higher and then it went down and then it started going up again. And so why might that be? So if we look at beryllium, no, I mean beryllium. If we look at beryllium, we would be taking an electron from here. But if we look at boron, which is what's illustrated, we'd be taking an electron from a slightly higher orbital. So the higher orbital means that that energy went down a little bit. Okay, so let's look at what happens as we move across the row. Why the ionization energy has this trend. Every time I increase the number of protons, so at the bottom I've got 5 protons, that's the nucleus pulling on these orbitals. Every time I increase the number of protons, there's a stronger attraction. And that stronger attraction is going to cause all of these orbitals to move down just a little bit in energy. So carbon's orbitals are a little bit lower. So if it's lower, the ionization energy, the distance to the top, is greater. Similarly, when I go to nitrogen, they get a little bit lower. And then I can keep moving across the periodic table and they keep going lower and lower till I get to neon and it's very low. But now what's going to happen when I get to my next element, nitrogen, or not nitrogen, sodium, Logan?
Is anyone that really high 3s orbital? Yeah,
I'm no longer taking my electron from the 2p's, which are very low down right now. I'm taking my electron from the 3s. So even though everything's a little bit lower in energy, it's a different orbital that this is coming from. So every time I switch what kind of orbital I'm coming from, I'm generally moving to a higher set of orbitals. And that's going to cause me to go down in energy because the orbitals are higher in energy. All right, so our exceptions, the blips on this trend, are that the third element in the period, where boron was, tends to be a little bit lower in energy. And that's because we're taking the electron from the p orbital instead of the s orbital. And the p orbitals are a little bit higher. And in the sixth element, and this is a little bit harder to explain. So the brief description is, this is where we're starting to pair our elements, or pair our electrons. And I'll get more detail in that in just a second. All right, you ready? Okay, so we talked about this already. The third element, boron, aluminum, et cetera, has a lower ionization energy than the second one. This breaks the trend. And this is because the electron is ionized from the p orbital, not the s orbital. The p orbital is less stable. Oops. Thought I had something underneath there. Let's go back. The p orbital is less stable, so less energy is needed to ionize. Remember, the word stability means lower in energy. So those lines representing the orbitals, when they are more stable, they are lower down. And then this is kind of an illustration of where those orbitals might be. The way that this diagram is set up, I couldn't make boron slightly lower than beryllium, but you'll have to pretend. So for beryllium, we have the 4 electrons. And for boron, we have the 5 electrons. So even though the boron orbitals would be ever so slightly lower than the beryllium ones, since boron's highest energy electron is higher than beryllium's, we have a lower ionization energy. All right. So we could also ionize something that is already an ion. So if I were looking at my second ionization energy for boron, now we have the same number of electrons for the 2 of them. The word for that is isoelectronic. Good vocabulary word. I like to ask that on quizzes. Isoelectronic means it has the same number of electrons.
And the same positions, right? So it's not, if someone's excited, it wouldn't be isoelectronic.
Right. But we're looking at everything in ground state for the most part. So generally that's going to be the case. So these both have 4 total electrons. Boron is going to have a higher ionization energy than beryllium. Its orbitals would be more stabilized. All right, so that kind of covers what I wanted to go through for the ionization energy. There's definitely more that we could say about all of those things, but not that's going to be relevant for this semester. So that's kind of the review I wanted to do on that. Oh, wait, I was going to talk about pairing energy. So there's one more thing I wanted to talk about. Okay, so this would be the configuration for nitrogen. Nitrogen has 7 electrons. The 2 in the 1s orbital aren't shown. They're way down, very stable energy, core electrons. But the 5 valence one are shown here. And so in chemistry, we often talk about a half full subshell or a full subshell being particularly stable. So the subshell is the part of that layer that has the same letter. So the shell is all of the 2 orbitals, so the 2p and the 2s. The subshell is the p, okay? So the 2p subshell is half full because we have 1 electron. Now, why are they all spread out like that? Do you remember that?
But the equivalent is 2 in different spin is more energy than it's spread out like that.
So that's why they all have the same spin.
And you can't put 2 in the same spin in the same spot.
And you can't put 2 in the same spin in the same spot. And we can think about this in terms of electrons are negative, right? So if they're both negative, do they want to be in the same orbital next to each other? No, they want to spread out as much as possible. Okay, and that's going to be tied to what we're going to talk about next with pairing energy. So nitrogen is half full. But if I switch to oxygen, we've got 1 more electron. Now, even though the orbitals go down in energy, we've got this sort of irritation here where these 2 electrons are like the siblings that are suddenly being told that they have to share a bedroom and they don't want to. These electrons do not want to be in the same place. So even though the orbital is lower in energy, we end up having a little bit of energy that we get back because of the pairing energy, because the electrons don't want to be together. So it should take more energy to kick it out, but because these sibling electrons, these 2 brothers are fighting over, whose side of the room is whose, it's just a lot easier to kick out one of those electrons than it should be. Okay, so pairing energy is the energy of having 2 electrons close to each other. And pairing energy is repulsive. You want to get rid of it. And that is why we have that blip in the 6th column for oxygen and sulfur in particular, and a little bit for the ones lower down, is that those electrons are so close in energy to one another that the atom would be more stable if we didn't have the electrons right next to each other. All right, so pairing energy, the electrons prefer not to be paired, and this makes it easier slightly to remove a paired electron. So I sometimes think of it like a tax refund, like you have to pay a certain amount of tax to get your electron out, but then you get a little bit of that money back because, oh, well, you're doing us a favor by relieving these 2 paired electrons. You took one of the electrons out of that orbital, so they're no longer paired. Okay, so there are a couple of other trends that are related to these, and we're not going to go into a great deal of detail on them. One of them that is in chapter 6 is the electron affinity. Electron affinity is like the opposite of ionization energy. So ionization energy says how much energy does it take to take away an electron? Electron affinity says, well, what if we're trying to add an electron? And it turns out that for most atoms, it's actually more stable to make it a negative ion, to put an electron on it. You would think neutral would be like the most favored thing. This is not true for noble gases. Noble gases never want to have another electron, but almost all the other elements do want to have another electron. So this chart has the electron affinities on it. If you can't read this, most of them are negative. So negative means it's favored to add an electron. The noble gases are positive because they do not want to have an electron added to them. But the trend has lots and lots of exceptions. So we talked about logical reasons for ionization energy to have exceptions. There are some logical reasons for there to be exceptions with the electron affinity, but there are more of them and it's more complex. So we're not going to worry too much about this other than to know that it's kind of the opposite of the ionization energy, that it's doing the opposite thing. All right. So we combine these two into what we call electronegativity. And this is what we're going to focus on in chapter 7. So electronegativity says, how much does an atom want to get rid of an electron? How much does it want to take on an electron? If I take those two things into account, I can kind of imagine if I put 2 atoms together, which one's going to be able to hold on to the electrons more than the other one. And so if I have something like fluorine, which does not want to get rid of an electron, really wants to take on an electron, and I have sodium, which doesn't really care if it loses the electron, is okay with taking on another one, but doesn't really care either, then fluorine's going to end up with the electron and sodium's going to be positive, and they're both going to be happy. But if I have 2 that are very similar, then they're going to share it more equally. So first thing to know about electronegativity is that the numbers run from 0 to 4. I don't know what the rationale for this was. Linus Pauling came up with this, and he kind of was the godfather of bonding. And so everybody was like, oh, we have to kind of do something similar to him. So even measurements that are not based on Linus Pauling's use a scale that's roughly 1 to 4. So fluorine is the highest. It's 4. Now, why don't we have the noble gases in there? In Linus Pauling's day, they didn't really think of noble gases as ever bonding. And so since this is specifically about how attracted electrons are in a bond, they just didn't include the noble gases.
But what if noble gases? What would you do with noble gases? What do noble gases have electronegativities?
They do have electronegativities, and so modern tables of electronegativities do include these. They are higher than the halogens, so the trend continues, just like you see it here, getting higher to the right-hand side. It would be higher for the noble gases. And in fact, we'll see in the next couple of chapters when we start talking about bonding shapes, xenon and argon are known to bond with fluorine, sometimes oxygen. Neon and helium don't really bond, but the heavier ones do. And krypton does, yes. Okay, so What is electronegativity? It describes the tendency of an atom to draw electrons to itself in a bond. So think of this as tug of war between the two atoms in the bond. Which of those atoms is able to get the electrons closer to itself? Because this is in a bond, we always want to compare this to other elements. We want to see what is its electronegativity compared to the other side of the bond. So if we have the same element, if it is homonuclear, homo meaning the same, nuclear meaning having the same number of protons, the same nucleus, then there's no difference in the electronegativity. The two atoms are fluorine, they're both 4, they're going to share equally, and we're going to get a covalent bond.
What if they were sodium?
If they were both sodium, then they would share equally. Now, we wouldn't call it a covalent bond, and we'll talk about why that is when we get to the 3 different types of bonding. Sodium doesn't form dimers, so it doesn't really have like two.
Forms like a crystal structure, right?
Exactly. Okay. On the opposite case, if we have very different numbers, then we would say they're ionic. So if we have something that is a 1, I think lithium is a 1, and fluorine, that's a difference of 3. And so we would say that's ionic. So people say, well, how close does it have to be? How small does the number have to be to make it ionic? And really that kind of depends on who you ask and what the situation is.
Phosphorus, fluoride could be considered ionic or covalent.
Depending on how different they were. And even if you look at carbon and fluorine, carbon is 2.5, fluorine is 4. So that's a difference of 1.5. And that's often used as the line between ionic and covalent, but that's not really an ionic bond. So hang on just a second. So what I want you to use is, what are the elements? Metal and non-metal, we're going to call that ionic, even if it's right in that gray area. If it's non-metal and non-metal, we're going to call it covalent, even if it's in that gray area. Okay, so some people draw the line at 1.8, some people draw the line at 1.5.
What if it's like aluminum carbide or something like that?
So I would call that ionic, but we're not going to look at that in this case. It's really a highly covalent ionic bond. So there's always like a gray area. We're going to avoid the gray areas as much as we can. Okay, so looking back at the electronegativity here, if I have, let's say, oxygen and chlorine, oxygen and chlorine there. You can't see those numbers, but that's 3.5 and 3.0. So the difference is 0.5, and so we would say that was a covalent bond, right? So let's look at that. Aluminum 1.5 and carbon 2.5. So the difference is 1. So that's really more in that covalent area. And so that's why, you know, it's kind of that, well, it's sort of a squishy sort of thing. We're not, we're not going to worry about those specific cases. So what if I was looking at anything that's in these 2 rows? Well, we have beryllium is 1.5, and that's the highest of everything in the S block there, aside from hydrogen, which is our problem child. So beryllium, which is an alkaline earth metal, with our first non-metal would be carbon, is 2.5. And so that's at that 1.0, which is kind of that same gray area. But beryllium is really pretty, quite a bit higher than most of the other metals in that group. So most of them are 1 or less. And so you can see that if you have something in the S block with a non-metal, it's pretty much always going to be ionic. What about these things here? We have palladium, platinum, iridium, rhodium, osmium. This set here, these 6 are called the platinum group. And then next to it we have gold, and those are quite a bit higher. Those transition metals behave a little bit differently. Gold is known for being used in coins, as is silver and copper. And then the platinum group are all known for being used in catalysts. So you may have heard of platinum catalysts. Sometimes they're used in catalytic converters in engines and things like that. And so this is because they have this high electronegativity, which is an indication that they do not lose electrons very easily. So these elements do not tend to form crystalline compounds that are like salt. They don't tend to form a lot of these ionic compounds.
What
So-
about gold carbide or some of these?
Like it can happen, but they don't tend to do that.
And it might be considered covalent at that point.
Right. So when we talk about, is this compound going to be ionic or covalent, I'm not going to offer these because that's not something that tends to happen naturally. What might happen more naturally is for iron, which is 1.0, to get together with oxygen. Iron and oxygen is rust, right? So 1.0 and 3.5, that's a difference of 2.5. That's ionic, okay? All right, don't worry so much about the top part about the water molecule. We're looking at oxygen. Oxygen is highly electronegative, so you can think of this is supposed to be kind of like Gollum in the Lord of the Rings, with the electrons being its precious. And you can't read what it says there. Give me more, I need more electrons, please, just a couple more. So oxygen, you got to remember, is very, very electronegative. Fluorine is the most, and then oxygen. No other elements compare to those two. But the next one, so fluorine is 4, and then we have oxygen at 3.5, and then nitrogen and chlorine at 3 are the next ones. Everything else is less than 3. So these are. Okay, so what happens if we get two covalent things together, but there is quite a bit of a difference? Then we end up with a polar bond. So electronegativity describes the tendency of an atom to draw electrons to itself in a bond. We already said that. And we're always comparing it to the other elements. So the big difference is the ionic. That's at the top. We got a bunch of electrons around the negative one and very few around the positive. And then if they're exactly the same, it's like the bottom where it's purely covalent, but often we're somewhere in the middle where we have a polar covalent bond. Now notice this arrow here. This is a very specific kind of arrow called a dipole arrow, and it's got a cross at the end. And we're going to see that both in here and in lab when you do your computer stuff in lab. This indicates what direction are the electrons moving. So the arrowhead is on the side that's more negative, and the plus side is on the side that's more positive. That's why I remember it as with that little cross. And then you'll notice these little squiggly things. This is a lowercase d in Greek, so it's a delta. And the delta negative means it's a little bit negative. It's not a full -1 charge, but it's more negative than neutral. The other side is delta plus. It's not a full +1 charge, but it is more positive than it is negative. So we can talk about the bonds as having ionic character or covalent character. And then when we have something that's kind of in between, like your aluminum carbide, we say, well, it has both. But in this case, we're worried about it having more ionic character. In this case, we're worried about more covalent character. So sometimes you'll hear me use the term character. So again, sometimes people say, well, how different does the electronegativity have to be for it to be a polar bond? Technically, any difference at all makes it polar. Usually people don't worry about the difference if it's less than 0.5, but the difference between carbon and hydrogen being 0.4 puts it right on that border there, and sometimes that's important. Not usually, but sometimes it is important. So when we get to symmetry, If I ask you if it's a polar bond, the only thing you need to wonder is, are they the same element? If they're the same element, it's a nonpolar bond. If they're different elements, probably the electronegativity is different, and therefore it's a polar bond. All right. So these graphs kind of illustrate the polarity in a couple of different ways. Let's look at the graph on the left. You can see vertically, we are looking at the percent ionic character. So the higher up it is on the graph, the more ionic it is. And then as we go across, we've got delta En. So what do you think En stands for? Electronegativity. And what does delta mean? Change. So this is change in, or the difference between the two atoms. So on the extreme end, we've got lithium fluoride, and I can't read what that is.
Potassium fluoride.
Potassium fluoride, thank you. So those are very different. And then down here at the 0 mark, we have chlorine gas, Cl2. So the bigger the difference, the more ionic character the bond has. And then we do have things that are kind of in this dividing line area, right? And so this book has decided if it's 50% ionic character or more, then it's ionic, and if it's less, then it's covalent. And when we talk about acids, we'll talk about hydrogen fluoride or hydrofluoric acid as having a particular uniqueness to it being covalent compared to the other gas or other acids. These graphs are trying to illustrate the height of this is the electrons, and these are supposed to go up to peaks, and they just kind of chop them off so they don't have to make really tall graphs. So you can think that as being a really tall mountain. And if this valley between them goes all the way down to 0, that would be ionic. They're not sharing the electrons at all. But if the valley in between them only comes down partway, sort of dips in the middle as if there's like a bridge between the two, then it has some covalent character. So here's some examples of that. If I've got hydrogen, hydrogen, or fluorine, fluorine, see this dip in the middle, doesn't go down to the bottom here. So that means this is where they're sharing electrons, here and here. Okay. This one, we also have a dip in the middle, but instead of it being right in the middle, it's showing that there's a whole bunch of electrons over here and less over here. And so that's when we have a polar bond, is when that dip isn't right in the middle. All right, so the water molecule has hydrogen and oxygen. Hydrogen has a 2.1, oxygen has a 3.5. So which one's more electronegative?
Oxygen.
Oxygen. Okay, so in the water molecule, here's our oxygen saying, my precious, it wants those electrons. It's going to attract the electrons to itself more strongly than the hydrogen. Hydrogen can't pull these in. And so as a result, water is a polar molecule. Okay, so we've basically focused on two types of interactions. The covalent, which is mostly going to be two nonmetals together, and both nonmetals are basically going to have high electronegativities, moderate to high. And then between a metal and a nonmetal. What's another way that we could combine these things? Because we have two nonmetals, we have a metal and a metal, or we could have our metal and a nonmetal, or we could have a metal and a metal, right? Okay, so this gives us our three basic types of bonding. So metallic is between two metals, and it says two metals as if there's two atoms. Metals don't tend to form molecules, which is why we're not too worried about them. They tend to form larger things. And we'll talk a little bit more about this sea of electrons in a second. Then we've got ionic between a metal and a nonmetal, and a covalent between two nonmetals. Now, if I'm given an element and I have a periodic table, how can I use the periodic table to determine if that element is a metal or a non-metal?
It's a metal, it's on the left side of the zigzag.
So this brown diagonal here that kind of forms a little staircase between the brown and the green, that's the zigzag that Hope is talking about. If it is to the left of those brown elements, it's a metal. If it is to the right, it is a non-metal. The brown ones are called semi-metals or metalloids. We'll probably not really talk about them too much, but if we do talk about them, we'll consider them non-metals for the time being. Okay, so that is how we determine which one is which. So if I were talking about a mixture of, let's say, calcium and strontium. So I've got Ca and Sr. Which of these three types of bonding do you think it would have? Metallic. They are both metals, right? And if I had a molecule that had phosphorus and sulfur in it, it would probably be which type? Covalent. Okay, so metallic bonding is the kind of bonding we don't normally talk about. Usually we think of bonding as being sharing electrons, which is what covalent is. Or we think about it being the attraction of the positive and the negative, so the opposites attracting between the metal and the non-metal. With metallic bonding, remember these are our biggest atoms, and the electrons are far away from the nucleus. So when the atoms get together, all of those really far away electrons are just kind of swimming around together. And so we say that there is a sea of electrons. So let's think about this image of a sea or water. Let's say you go to the beach, to the sea, and you're in the water, and somebody else comes in. You don't say to them, oh, I'm sorry, that's my water molecule. You cannot use that water molecule. You keep your water molecules, I'll have my water molecules. They all just kind of flow around, right? Everybody uses all the water molecules. It's like communism, right? Metals are communists. They all share everybody's electrons. And this is why we get conductivity. Because if I apply a current here, these electrons that are around here can move very easily across here because it doesn't belong to any particular atom. All of those atoms are just like, as long as I got some electrons near me, I'm good. You know, so it moves along, and this atom doesn't mind because there's some atom over here that's going to give it some electrons. Okay, so we get conductivity because the electrons are very loosely held because the atoms are very large. So remember I said that size is going to impact a lot of these things. The reason why big atoms are metallic, metallicity is defined by conductivity, and the large atoms have those electrons that are far away, so they're not attracted. The ionization energy is teeny, teeny, tiny, and they can just travel along from one atom to the other. Okay, so I will ask you on a quiz or a test to describe the differences between ionic, metallic, and covalent behavior, but that's probably the extent to which we will deal with metals, metallic behavior. Now, metals don't tend to form molecules, they tend to form crystals. So even though the little blue electrons in there are kind of all over the place, you'll notice that there's a very regular pattern of these bigger red dots. So that's illustrating that they're forming kind of a crystalline structure there. And ionic compounds tend to be very similar. They tend to form crystals. So we call those extended structures or crystals. Okay, so let's look at covalent bonding. We're going to come back to this graph here. But covalent bonding is based on, are the two atoms more stable if they are together, or are they more stable if they are apart? So if they are together and they're sharing electrons, and that's more stable, then that's going to form a bond. So how do we know if it's more stable? Stability is lower energy. So this is an energy diagram, the energy here. This is showing how far apart the atoms are. And we can see this graph shows that it is very low when they are close together. Now, why does it go up really high? because if we're at the 0 mark, this means that they're actually physically occupying the same place. You have 2 nuclei on top of each other. That would not be fatal. But getting close enough to share electrons, this is lower energy. We'll talk about why that is in a little bit. We'll come back to understanding that graph a little bit better later on, probably on Wednesday. Okay, so I had said metallic, we're not going to worry too much about. Differences between covalent and ionic, we do look at. So we've got this triangle and En. What do you think En stands for? Electronegativity. And what does the triangle mean in chemistry? Change. So in this case, it means the difference between, the change from one atom to the other. If I have a very small difference in electronegativity, I'm thinking covalent. If I have a significant overlap of electron density, so that's what those 2 cone graphs were when they were overlapping each other a lot, that would be covalent. When they were far apart and the dip goes all the way down to the bottom, that would be more ionic. So covalent bonding tends to form molecules. Anytime we have molecules, we're thinking covalent bonding. When we have crystals being formed, that's more likely going to be an ionic interaction. Those extended structures. Now we can get crystals of molecules, so that's another story. I need to rephrase that. They do form crystals, but they form extended structures, repeating patterns of atoms, is I guess what I should say. All right, so a covalent bond, in order to break or disrupt a covalent bond, you have to put in a lot of energy to pull these 2 things apart. And we'll keep coming back to that throughout the semester about how covalent bonds are very strong and it's very hard to pull them apart. For ionic, it's going to depend on how big the charges are. So it's often easy to just have a polar solvent like water, and that can get in between them. So you don't have to put a lot of energy in order to dissolve sodium chloride. Sodium chloride table salt. We can get water molecules in between the sodium atom and the chlorine atom very easily. So much less energy to break apart that ionic interaction than the covalent interaction between the hydrogen and the oxygen. Now, in contrast, if I had very high charges, like if I had aluminum is a 3+ and oxygen is a 2+, that's a much stronger interaction. That's harder to pull apart than the sodium chloride. But generally, our covalent interactions are going to be the strongest. And then how are we going to know 2 nonmetals versus a metal and a nonmetal? All right, I think, yeah, we already talked about this. How do you know your metals? Your metals are left of this zigzag line. All of these are metals, and we just have very few nonmetals. All right, so on Wednesday, we will talk a little bit about the size. We talked about this a little bit in the previous slideshow. And then we'll get a little bit more into bonding.